The first speaker in the afternoon is Andrei Okounkov, who will tell us about duality interfaces and three-dimensional theories.
Thank you so much. I want to thank the organizers for the chance to address this this marvelous audience. So this is in this work with Mina, we study indices in supersymmetric theories in 2+1 dimensions, where the space is some Riemann surface B. I guess I'll be pointing to this slide. And the time is made periodic. So S1, and we're not the only people who study these indices. There's there are other teams of people who do it, and maybe I'll point out maybe the main differences in how we think about them. And so, by its very nature, index may be computed for any deformation of your theory. In particular, you can compute it in the infrared, means your B gotten very, very large, and the states in your theory for B very, very large, well, they have to be almost the states in the infinite volume, that is to say vacuum, but slowly varying as a function of space. So this is like modulated vacuum. And so then instead of some theory we don't know, we can think about sigma model with target the space, the moduli space of vacuum of your theory. And the theory we want them to with 8 supercharges, and then that moduli space of vacuum wants to be a hyperkähler manifold, but in reality it's not quite a hyperkähler manifold, more like a singular algebraic symplectic variety. And I want to point right away that we don't study them completely supersymmetrically. That is to say, we study indices with respect to group action, equivalent indices with respect to group actions on X that not only preserve but also scale the holomorphic symplectic form. So the weight of this holomorphic symplectic form will be an important parameter in the theory. And so this is in case your theory is a gauge theory, there is a very nice, in algebraic geometry, differential geometry, in physics, there is a very nice moduli space of that you associate, namely what's called the space of quasi-maps, or vortex solutions of the gauge theory in physics language. And so the data of a gauge theory is just an arbitrary gauge group, an arbitrary symplectic representation of the group, and then in this case X is algebraic symplectic reduction. That is to say, you take you set the value of the complex moment map to be 0, you take the stable locus, and you take the quotient by the group G. So in physics language, you said restricting to the stable locus is the same as setting the real moment map to be something. And so these are the moduli spaces with which we actually work. And I think it's a very important geometric question, and also actually a physical question, to invent the right moduli spaces for the case that for more general theories. So that's a challenge in algebraic geometry and physics. And what we're really computing are virtual indices of Dirac operator on this moduli space. So this is this moduli space of concretely quasi-maps from your base curve B to this moduli of vacuum X. That's some countable union of algebraic varieties, very singular ones, but the virtual index of Dirac operator on them may be defined. And in fact, so you really compute it not as you don't need to think about the actual differential operator. It's enough to think about, since we're computing the index, it's enough to think about the K-theory class, the virtual A genus that is supposed to represent it, which it may be defined in the K-theory of these moduli spaces. And this is much more subtle than the virtual fundamental class, and so in algebraic geometry there are many different moduli spaces. The existence of Dirac operators, the existence of favorable properties of this virtual A roof genus is a much more subtle question than existence of a virtual fundamental class. And so, these indices, like I said, we study them. We study them as graded vector spaces, and they graded by what? First, there's a group action. So there is a group action here. We study maps from B to X, and so if X has some automorphisms and B has some automorphisms, this will act on everything, and this will act on indices. And also this moduli space, it's a countable union fine-dimensional algebraic variety indexed by the topology of the map, and we keep track of this degree by introducing new variable z, which we make to keep track of the degree. And where that variable z actually lives, it sits in a torus which you associate to the Picard group of X. So you have a pick of X is, I don't know, say 5-dimensional. This will be a 5-dimensional torus. And that's where that variable z sits, and that keeps track of the degree. So these indices are like I said, well, okay, they're traces, they're functions on the covariant variables, the group variables that take value here, and these variables that we keep track of degree we call the Kähler variables. Okay. And one can allow the surface to have marked points where you would put insertions that would be line operators in 2 + 1 dimensions. And then the space of these possible insertions is as big as the K-theory of X. And then when you have n marked points, that means you can put n insertions. It means your counts really take values, really take an input from here or take values here, so n copies of K-theory of X. And they together form like a K-theoretic analog of cohomological field theory, meaning if your curve is degenerate, if it develops a node, then the restriction of that index bundle to this boundary strata in the modular of curves, this can be reconstructed from lower genus. The only difference with cohomology is that the metric you use when to glue this, so the metric you compute as a 2-point invariant on a sphere. So something in kx, 2 copies of kx, and that metric, it's not the Poincaré metric, it's something that depends on the degree variable z. It's some non-trivial metric. People call it a glue metric, but it's independent. It depends on z, but doesn't depend on the automorphism here. But it's some metrics. And one certainly expects, although the specialist will tell me, I didn't check the details, one certainly expects that general reconstructions theorem of Galen-Telemann type would apply, and this will produce this as so what is this index? This index is some virtual bundle over the moduli of pointed curves, and given Telemann style reconstruction tells you how to produce such bundle from very little data, and I have no doubt this will apply here. And in some sense, it's this K-theoretic field theory that is the complete description of all indices, and everything else is when we cannot define the curve counts, we sometimes may define just that. So that's the. And so, in the guiding star in all this business is this phenomenon of 3-dimensional mirror symmetry, and I'm exceedingly honored to see the father of this sit and listen to my humble lecture. And so, and what it predicts is that some pairs of this theory are exactly equal. We already just talking about indices. We're not talking about the actual theory. Theory is just the indices. The indices as virtual bundles over moduli of curves, those are exactly equal with the exchange of the Kähler variable z and the covariant variables, but not all the covariant variables. We take, like I said, we take automorphisms of X, and in principle we allow them to scale the symplectic form. And so we will break all automorphisms of X into 2 groups of variables. One variable is just the weight of the symplectic form, whatever scales the symplectic form. And then there's a subgroup that preserves the symplectic form. So that's this torus will be noted A. And so these two tori are permuted on this 3-dimensional mirror symmetry. And then of course you have to identify the insertions, because insertions in one case take values in the covariant K-theory of X and power series in Z, and on the mirror side it's the other way around. So you have to really specify how you identify these two spaces. But that'll be uniquely fixed by what I'm going to say later. And this is extremely powerful, and also something which is Mina and I can actually prove in the situation when both counts, like I said, with current technology and algebraic geometry, you can define this count only in some limited number of cases, but when it can be defined, then we can actually prove this equality. So for instance, if I compute any covariant count in algebraic geometry, that is, what is it? It's Euler characteristic of some sheaf. If everything was compactly supported, that this Euler characteristic is just some virtual representation with symmetry groups, so it's a polynomial in the covariant variables. And if it was not compactly supported, then it will be still a rational function with very well understood poles. And then in particular, the very first consequence of this three-dimensional mirror symmetry, it says that the dependence on scalar variables should be also rational. So it's kind of amazing for people who do these curve counts, when very often we can't really prove they even converge, but in fact here not only they converge, but in fact converge to a rational function. And that's something one can, it's, there's a good mathematical understanding of this rationality, and many cases of that can be established, including what's the famous of that rationality. Then you compute the dt invariance of a threefold, and forgive me for saying that the threefold does not need to be Calabi-Yau for these counts to make sense, and we compute them with any insertions and anything that is still a rational function of the variable that counts the number of boxes, the Euler characteristic of your sheaf. That's a kind of a basic conjecture in Donaldson-Thomas theory, and so this rationality and that rationality are very directly interlinked. Of course, when people respond differently to rational functions, people have various ideas about them, and it's not very easy to find the right. It's just given a rational function, not so easy to find the right point of view, and it's better to go through more complicated functions to really nail things down. And so that will be our strategy. We'll introduce more and more complicated functions to actually identify these rational functions. And as a first step, we will do like a Nekrasov function analog in this situation. Namely, we'll take why study theory in some arbitrary space where you already have the physical space, which in this case will be just a flat plane, and one can count states in that plane if one works equivariantly. It's like a Nekrasov theory. If one works equivariantly with respect to rotation of the plane, that's a well-defined count. Right? And this in math, this moduli space. So how do you define these counts in Nekrasov theory? You take maybe a Limback quantification. Then you extend your instant onto infinity. That's one way to do it. And in similarly here, you really think of this moduli space as maps, as an open set inside maps from P1 that are non-singular to infinity. That is the right moduli space here. And so we call them vertex functions for the reasons that they reproduce this vertex function in Donaldson-Thomas theory. It seems like a good name, and somehow related to vortices and vertices, so it's somehow good. And then what are their functions? What sort of input they take? They can take one or two inputs. We will talk about just one input. If you have a map from the plane which is non-singular to infinity, means has some value at infinity, means from this moduli space you have a map that to X itself just evaluates your map at infinity. And then then you can push forward your index sheaf under this map and get an element in the K theory of X. So that will be just some element in K of X depending on all the covariant scalar variables and this new variable Q, quite analogous to Nekrasov function. But you can also put an operator at 0, which is another point preserved by this rotation, and then you get two objects, so that will look like an operator. And both points of view are useful. So So these are not rational functions. Similar, of course, Krasnov functions are not rational functions. These are not rational functions. Instead, they solve Q-difference equations in all arguments, and the equations with rational coefficients. And the physical argument for that is that you can say what the matrices of these equations are in terms of subcounts on P1, and therefore they should be rational. Because in math, the argument goes exactly the opposite. You first study the Q-difference equation, and then you deduce stuff about P1. And that's analogous to the quantum. It's like a difference analog of the quantum differential equation. So that must be very familiar to people here. The nice feature here that this, in fact, in most of the variables, like in the variables z and the variables a, this equation in fact have regular singularity. I mean, many kind of maybe in a relatively strong contrast to what you used in Graham-Witten theory, where you deal with Stokes factors and stuff. That this equation with regular singularities. And in fact, these vertex functions you can think of them as a very fancy generalization of Q-hypergeometric functions. And for the simplest examples I've been keeping here, this exactly is the Q-hypergeometric function. So I keep drawing X as a cone, as a quadratic cone, or you can think of those also, it's a blowdown of T star P1. If you blow up the vertex of this cone, you're going to get T star P1. And if you count curves there, then what you're going to get up to some perturbative factor similar to what you get in Nekrasov theory, there will be this very nice series where you have the coefficient of degree D curve that comes with these 4 Pohammer symbols, where each Pohammer symbol is just whatever the Q factorial power of x. It's this product. It's product 1 minus x, 1 minus qx up to and so on d times. And the variables, what are the variables here? A is the variable. The automorphisms of x preserving the symplectic form are, it's easier to think here. Any automorphism of P1 will preserve the symplectic form, so that is a matrix 1A in PGL2. And then H bar is the weight of the symplectic form. So these are the automorphisms that preserve symplectic form, and then there's a weight of symplectic form. So that's the series. And then of course I should warn you that this kind of 19th century charm of this Q-hypergeometric function, that is rather misleading because if you write something like this for more general X, you're going to find a whole zoo of different animals, and then. Actually, while thinking about this talk, I learned that the word monster and the word demonstrate is actually come from the same root, and that's a monster is something that heaven used to demonstrate people certain phenomena. Anyway, so in particular, the first animal beyond the classical thing you'll find has to do with the Hilbert scheme of points, and then the vertex function is really just this one-leg vertex in the full K-theoretic Donaldson-Thomas theory, and which is why we use this name. And more complicated ones contain all the 2 and 3-leg vertices, and I don't know. I'm not going to ask you raise your hand if you ever computed with these objects, but if you did, it's not it's not a simple object. So it is quite remarkable that this Q-difference equation is actually a very effective way to both compute and think about this object. So it's quite remarkable this Q-difference equation actually known in some generality in terms of some geometric representation theory. And I want to point out that, in fact, so this it's a basic fact of life that if you have a Q-difference, if you have a function solving a bunch of Q-difference equation, and if you know one of them, that essentially you know them all basically, because it's any Q-difference operator in some variable commuting with your operator is more or less uniquely constrained. So that's it's enough to know any one of them. So, but in fact they all know in some generality. And so, for example, for the Hilbert, again, for the aforementioned Hilbert scheme of endpoints, the equation with respect to the one and only Kähler variable there, that's the Q difference version of the quantum differential equation for the Hilbert scheme of points. That's an older computation of Rahul and I. And this can be done explicitly, and this in fact is for every quantum group, there is something people might call the dynamic. So if you have a quantum group, there are two kinds of Q-difference equations associated to this quantum group. There's something people call Q-Knizhnik-Zamolodchnikov equations, and there's the dynamical equation, so that will be the dynamical equation. And the group is this, again, to this first new geometry, there's this first new kind of quantum group, and that's quantum double loops into GL1 head. Oh, sorry, quantum double loops into GL1. And what I was going to say. So that is the Q-difference version of the algebra from David's lecture, and that's a remarkable algebra. It appears in math and in many different ways, in many different disguises. People have different ways to think about it, but anyway, in terms of in terms of this algebra, you can write the actual Q-difference equation for all these guys. And so 3D mirror symmetry with respect to 3D mirror symmetry, the Hilbert scheme of endpoints, that's supposed to be self-mirror. So the equation in Z and A, this variables Z and A should be the same, which is true. But it's not something you prove by inspection because, like I said, the equations themselves, I mean, they're beautiful, but not non-trivial. And the best way to think about proving that the equations are the same is to first prove their monodrome is the same. That's the key step. And what is the monodromy of Q-difference equation? Monodromy of a Q-difference equation is something much simpler than the monodromy of usual differential equation. What? Doesn't matter. So what it is, you compare. So this is monodromy is always comparison of different solutions, but here you compare the solution you get. So you have a Q-difference equation. So it means it's an equation with respect to shifting Z by Q. And that has two fixed points, Z equals 0 and Z equals infinity. And you take the equation, the solution that you find near 0. So an example of this being this one, it's a solution of whatever equation it solves. So these are two effects. So this is the quantum difference equation for T star P1 is the hypergeometric equation. It has two solutions, and the two solutions look like this, depending with plus and minus. There are two solutions. And so you take this guy, which is holomorphic near Z in the punctured neighborhood of Z equals 0, and you compare it with the similar guy at infinity. Both, by the virtue of Q-difference equation, both extend to a meromorphic function in the whole complex plane. And then you just compare these two meromorphic functions. And so there's a picture to illustrate. So this is CP1 in which my variable Z lies. I'm studying equation of the form psi of QZ equals S of Z times psi of Z. And then there will be a solution which is holomorphic near 0, so in some punctured neighborhood of 0. And then by the virtue of Q-difference equation, it extends to meromorphic functions with singularities which have to come from the singularities of the equation. And similarly, so they form geometric progressions that go off to infinity. These are the singularities of the solution near 0. By the same argument, there will be a solution near infinity, and its singularity, again, it will be holomorphic in the neighborhood of the infinity, and then it will have singularities accumulating to 0. And the monodrome is just the ratio of these two fundamental solutions. And the basic feature of that is that this is a constant function with respect to my equation. It means this is invariant under taking z and replacing by qz. So it's a matrix of elliptic function in ordinary language. So it's a matrix, monodromy of Q-difference equations, a matrix of elliptic function. So if the map from the equation itself to the monodromy here, it's some transcendental map between algebraic varieties. It's somewhat analogous to like exponential map between Lie group and Lie algebra and Lie group. And in general, you study it as such. It's some transcendental object. But in our case, we can actually compute it due to the following reason that I'll explain. So this is if you again, I recall that if I have for compact curve B, the 3D mirror symmetry should equate the counts of curve in two mirror geometries with the change of variables. But for non-compact curves, it only equates the equations, not the solutions. That clear? Like it's clear that if this function cannot be symmetric, these functions cannot be symmetric in Z and A for the simple reason that when you look at this function, in Z, it's holomorphic in some neighborhood of 0, so it has no poles near z equals 0, and then the poles appear and accumulate to infinity. Whereas in A, it has poles all over. So there are two solutions here, and one of them gets poles accumulating here, and one of them gets poles accumulating there. So the fundamental solution of this equation near z equals 0, this is something what we call the z solution, and there's no way it can be equal to the A solution, just because the singularities of them are different. Yeah? Make sense? It's actually kind of an interesting point about Q-difference equation is that it's possible for a Q-difference equation to be separately regular to sets of variables but not jointly. This can never happen for differential equations. It's a basic consequence of a deep theorem of Deligne. But here it does. So you have two groups of variables and you have two different kinds of solutions associated to them. And so they're defined on the same set. They don't have different domains of definitions. And so you have two different kinds of solutions with the same equation, and therefore they're also, like in the monodromy problem, they're related by some elliptic matrix, which we call the pole subtraction matrix, because it really takes poles in one variable to make it poles in the other variable, some matrix of elliptic function. And so maybe I can compare and contrast this monodromy with the pole subtraction matrix, because they kind of look, if you look at them from far away, they look the same. They're both elliptic matrices of elliptic function of the same size. They compare two different solutions of the same equation. But one is some global analytic object, means to go from a matrix, from equation to its monodromy, that's a transcendental map and requires some global knowledge. Whereas to take poles and trade them for other poles, it's just completely local computations, completely algorithmic. And that is an explicit algebraic procedure. Because all you do is you're looking for elliptic function with given zeros and poles. That's just algorithmic. But the most important point that the pole subtraction matrix constrains, I should have said constrains, it says contains, but it constrains the monodromy as follows, namely, what is monodromy? You have to compare the solution at near z equals 0 to solution at z equals infinity. Well, let's convert them both to solution near a equals 0. So the solution, so you had solution, the z solution, we converted it to a solution, and we can convert it to the same, we both go to the a to the 0 solution, the a solution with a is 0. Means that solution has the form that is some series in a, and then the coefficient some function of z. Like the monodromy, but now we're asking what's the monodromy of this function? What's the monodromy of this function as z goes from 0 to infinity? Well, it's the same as the monodromy of just psi z, but psi z solves the a equals 0 equation. So the bottom line the bottom line in this argument is just the monodromy at the value when a equals 0. So it's essentially a trivial thing when in many examples of interest. So maybe I'll explain it like this. So again, I have my roughly square of different variables. Here run my Kähler variables, and here run my equivariant variables. And what does it mean to set some of these variables to 0 or to infinity? Well, if I set the Kähler variable to 0, it means I kill the quantum corrections. I don't do any curves. I just do some easy computation, like it's just classical computation, k3 of x. But if I set the covariance variable to 0 and infinity, then all I'm doing is I'm computing curves in the fixed locus, which is a priori very much simpler varieties. Very often it's a point. Very often that variety is just a point, and there's nothing to compute. So, in other words, this equation, both equations dramatically simplify if I restrict to extreme values of parameters, and then this means this previous square here, that is actually that is the computation of the monodromy. And so now you might be lost, and then maybe we refresh do a refresher. So what was the plan? The plan, we wanted to compute first. We got this fly to. We followed the fly that made us want to compute some rational functions. To compute these rational functions, we swallowed the spider that says, well, let's do instead solution of Q difference equations. Okay, to get the spider, what was the? I didn't, what's the next animal you swallow? But anyway, we swallowed subsequently bigger and bigger animals, and that we wanted to say, well, to compute these difference equations, we want to instead compute their monodromy, which is, so we started with rational functions. Then we said, okay, let's do hypergeometric type functions instead. Then we said, okay, let's do elliptic functions instead. Let's think of the monodromy of these Q difference equations. And so now we've introduced this further matrix that catches monodromy. And then, so now comes the horse, which means the problem die, is that one can compute this pole subtraction matrix that expresses the monodromy. One can compute in synthetic terms. This is, so maybe I'll go back here. So somewhere in the bulk of this picture, we're trying to count curves in X. Whereas when A equals 0, we're trying to just count the curves in the fixed locus. And so the pole subtraction matrix knows something about the relation of the fixed locus to X. And what this matrix is just the right class of attracting manifold. Just like in Nigel's lecture, there was some attracting manifold, and that attracting manifold, there's one and only object you can associate to its class in elliptic homology. Okay, and how you should think about it. So imagine you have some symplectic manifold X, and have a torus action. So the torus action will have some fixed locus. There might have many components, just like in the previous lecture. And then the orbits of this action, well, there could be, if I look for the particular component of the fixed locus, then would be attracting manifold, like attracting manifold of this fixed locus, but its closure might be, something complicated, might intersect other components in some complicated way. But the point is, in elliptic homology, there is something absolutely canonical you can associate to this object. I mean, it's kind of a miracle that the fact exists. So elliptic homology is it's a scheme associated to X in some covariant way. The spectrum of elliptic homology is some scheme. I'll drop the word spectrum. And elliptic homology class is a section of a line bundle on that scheme. And the fact that this sits on an attracting manifold means that section has a certain support. And the fact that there's the fact that there's the line bundle plus its support, that uniquely characterizes the section. And so there's only one and only thing you can do in elliptic homology to to associate here. And you can ask, well, how can this depend on scalar variables? The point is that the line bundle elliptic homology is some scheme which is like a union of a billion varieties. So in particular, it has continuous families of line bundles, and line bundle itself depends on this variable z. So that object, therefore, depends on all the variables we want. It depends on the covariant variables, like any covariant homology class is supposed to, and then it depends by the virtue of also being a section of a line bundle that depends on z. It also depends on z. And so it's, I'm not going to go through definition what it is, how you set up things in elliptic homology, but I find it's amazing that you can reduce quantum curve counting problems to completely classical computations. So just some essentially very classical questions about it. So, like I said, this elliptic homology, when you look at it, well, what is covariant elliptic homology of X? It's some scheme which is basically a union of a billion varieties. And you're asking for a bunch of elliptic functions that glue together according to what the union is and have a given automorphic. That's all there is. So, and so this is so that was. I realize much of this may be new to you, but there's also, but it's not strictly speaking new thing in math. This is not what this talk is about. This is like a background. So now we're gonna talk about actual subject of the talks. Now we're gonna start now. Okay, so maybe the takeaway from the previous slide is there's some kind of remarkable correspondence in elliptic homology between the fixed logos and the whole variety, and that correspondence solves many questions. Like, for example, it gives you what the actual indices are. Okay, so now what this talk is about is that there is a very transparent physical and mathematical interpretation of what these elliptic stable envelopes are in terms of, if you think about boundary conditions, your original three-dimensional theory. So what are boundary conditions? Boundary condition is some theory. So suppose I have a curve with a boundary. And so there's some fields, some theory that will live on the boundary, and then the boundary is times the time circle that will couple to the bulk theory. That's what it means to have a boundary. And so this boundary here is one circle cross another circle, so together they form an elliptic curve, or at least a torus. And the elliptic homology of X is basically one version, maybe the only version, of what is the K theory of the category of boundary conditions for this three-dimensional theory. Okay? And so if we assume, now I apologize if this picture doesn't correspond to your idea of normal life, but if you're offended, I profoundly apologize. But in particular, suppose you have two. So we're talking about two theories that are just really the same, except the words that we use to describe them. It'd be called different things in different languages, but the essence here is the same. The life is the same. The words we use is different. And so when this happens, then there's a particular interface between the two theories on which just the words change. The life doesn't change. Right? And so that's you can call it the duality interface. And in particular, what it should do if we attach it, so we were computing this Nekrasov style vertex functions. We were computing them on P1, but the condition that nothing's going on at infinity. What will happen if I attach that if I impose this interface near that infinity at P1, at the infinity of my C? Well, this means it will have to turn things which were Z solutions before to something in the mirror language will be the A solutions. Okay, make sense? And so maybe I'll come back here. It just means there is what is the interface? The interface is supposed to be, if you think of its K-theory class, that's supposed to be an elliptic class on the product of X and X check. Right? Because you come here we have the theory with X, and its boundary condition is elliptic. What we can put on the boundary, at least the K theory of that, is the elliptic homology of X, and on the other side we put something from elliptic homology of X check, and we can couple them together. Means we have a class on the product. And this class has to turn fixed points into, has to turn Z solution into A solution. That is to say, it has to turn fixed points of the torus action into stable envelopes. That is to say, that has to be a class on X cross X check, such that so it's an elliptic homology class on X cross X check. It's a section of some line bundle. It has a certain support, and support is has to do with attracting manifolds in both geometries. But its crucial feature should be that it's when you're restricted. So this is a class on the product. If I restricted to a fixed point in X. So if I restrict to a fixed point in X, I get a class on X check, and that should be the elliptic stable envelope for X check. And if I restrict it to a point in X check, then I'll get a class in X, and that should be elliptic stable envelope for X. But then you realize that this condition, it's enough. Either of this condition is enough, and in fact, they're both just what it says, that there's a class on the product with a certain support and a section of a certain specific line bundle. The point is that line bundles on X checks are parameterized by covariant variables for X, and the line bundles on X, on elliptic homology of X, are parameterized by covariant variable XX in X check. And so there is one God-given, like Poincaré style line bundle that sits on the product of this elliptic spectrum of elliptic homology. And we're looking for a class that's section of this line bundle with a given support. And again, it's elementary to see it's unique. And the only question, if there is one. So if there is one, then by this uniqueness, it has to have this property that it's restricted to fixed points in one and gives the stable envelopes in the other. And then it proves that the two monodrom, this automatically proves the two monodrom is the same, the two difference equations are the same. That somehow, from this, it's automatic. Because you compute the monodrom in these terms. And clear? And we denoted M for the class that reproduces everything. This is to say the mother class. And in fact, you can do it rather abstractly. I don't want to go in details. You don't really need, strictly speaking, X and X check. It's enough to have two schemes with enough maps between them so that they make them look like the spectra of elliptic homology. And then, so what are the maps? The map is you have elliptic homology of X, which I maybe denote by this curly E. That is by its structure of equivariant homology, mapped to the homology of a point, which contains my torus reduced mod Q. But if I think about the Chorn class of line bundles, they will give me a map to a variety which is dual to Z mod Q. So, because for every line bundle, I get elliptic Chorn class, which is a home from my guy to C star mod Q. And so if I just have this data, and then I can say what is this mother class, and what this mother class should be, and if I exist, that this pair of dual things is somehow I can reconstruct the monodromies, the commuting difference equation, and from them given tau Telemann, I can actually reconstruct the whole K-theoretic field theory. I don't really need to know what X is from this. I just have this. But the existence of this class, as I said, the existence of this class is super not obvious. And so for gauge theories, there's something we can prove. So for gauge theories, when both X and X check are both gauge theories, which is due to folklore or maybe somebody's theorem is equivalent to the fact that fixed points are isolated on both sides. So anyway, let's assume they're both gauge theories and fixed points are isolated on both sides. Then let's say X and X checks are mirror if the points in one are mirror to so if I have a point that it's mirror to a vector space, and that vector space is just the tangent space to the fixed point on the dual side. If that is meaning that certain the quantum difference equation for a point is some 1-by-1 difference equation, and then this is the same difference. This difference equation is the same as the weights of the torus action on the tangent space to the dual point. So it's some elementary condition to check. And so upon this hypothesis, this class M exists, and in fact the two cohomological field theories are equivalent. That's something I believe we can prove. Although I put a star since it'll be a while before we write it down. But here's an example. For abelian theories are classified by just exact sequences, dual exact sequences of tori. So if I have a torus acting in n-dimensional space, then if I have any subtorus and quotient torus, then I can form X to be the reduction of T star n by T1, the subtorus, that will be X, and the check would be I'll take the dual picture and reduce and I reduce algebraic simplicity reduction by the dual of T2. And then the mother class is something, the one and the only thing. It's like the Fourier Mukai kernel on pair of dual abelian varieties. You just you have the coordinates on the torus, you have the coordinates on the dual torus, you take the theta function and the product. That is an elliptic homology class. It's also like a Fourier Mukai. People, anybody who's ever thought about an abelian variety would love this formula, or at least understand. Love maybe too much. And then there's explicit formulas people have been working on, making them explicit for non-abelian theories. And maybe to finish, maybe I'll say a word. I wish I could say more, but I was just gonna. There's some, even our very first paper, there's some cryptic remarks towards this end, and this will probably stay a little bit cryptic. And that, so how you can think in algebraic geometry, about boundary conditions for maps? Well, the easiest thing is just take the boundary of infinitesimal size. Namely, if I look at the space of maps that are holomorphic outside of a given point and have pole of arbitrary order at this given point, so that's like maps from that's a maps from B. Take away the point, and then from this I can just expand this map into what's it called? Laurent series so T, if you assume T is the coordinate, T equals infinity is the coordinate of this point, and I can expand this map into Laurent series in this form. Laurent series of that kind. And so then I'm gonna get a map from this moduli space to some kind of loops, namely maybe the quasi maps from the spectrum of this formal power series ring or just to say from the formal punctured disk to X. And in fact, I'm going to go to not even here, but rather to universal cover, because if I actually have a map outside, if I have a map outside of this formal disk defined, then in fact I have a point have a canonical lift to the universal cover. And so then the Tate version of this elliptic homology means when your elliptic curve is the Tate curve, namely you work in formal power series in Q, what that should be associated to. So maybe denote this space, this whole space denote Lx, it's some version of universal cover loops in X, and so that's at least like I said, the Tate version of covariant elliptic homology is just a covariant K-theory of this moduli space where Q is the variable that acts by rotating this variable T, and it's very natural to assume that the right category of boundary condition are the right roughly Lagrangian quasi-coherent shifts there. And then, and on this loop space, there's a lot of group action. So there's Q, the action of Q by loop rotations. Then there's action of loops NA, inside of which we can take the co-characters. There's the action by deck transformation, which is the group of, so we took universal cover, so they're deck transformation. These are the characters of Z. And then that's on the space itself. And then if you take equivariant shifts, they can further act by equivariant twists. Since we take a equivariant shift, so there's an action of, we take action of, we can twist shifts by characters, and then the line bundles on this variety are parameterized by co-characters of Z, so that will be twist by line bundles, and we expect the mother class to categorify to an equivalence between the two categories of boundary condition that correctly intertwines these two actions. So, well, it's 251. I apologize. So that's where I want to end. Yeah.
It's been 2:51. We still have time for questions. Questions? Yes.
Andrei, just a comment near the end. It sounds like this category might actually be line operators, including disorder type line operators that have singularities. So far, in describing lines as equivariant K-theory classes, that gets about half of them. And so in these theories, there is a category of line operators, and it does look like coherent sheaves on the loop space.
On loops?
Yep. In a holomorphic twist of these theories.
That's useful to know. But the loop rotation, what it gives you to the loop rotation variable, what does it give in this category?
I mean,
what?
I'm not sure I understand. I mean, there's an action.
Right. What does this variable mean for you then? Like, well, how?
I mean, it's literally loop rotation. Right? It's rotation around the insertion point of the line, just like in your picture.
Okay. And the K-theory goes to where? It goes to elliptic homology of your category? Anyway, it sounds like something we should discuss. Yeah.
Another question.
Yeah. So you mentioned Geventhal-Telemann theorem for K-theoretic field theories, but in the usual version, I think you need to know the Madsen-Weiss theorem, like the stable cohomology of MG. If you wanted to prove this in K-theory, wouldn't you have to know the stable K-theory of MG?
If you do topological, that's you can just put one into the other, and then yeah. Look, I said clearly I don't consider myself an expert on Geventhal-Telemann business, but.
Yes, another.
So one of the hallmarks of this mirror symmetry is that there's a non-abelian symmetry in the game, and only the Cartan subgroup of it is visible on one side or the other, or neither. Do you get the surprise is that the emergence of the non-abelian symmetry group that acts. Do you see any sign of why it happens from this construction? So these Z's are associated with some abelian group.
Right.
And it's often the case that it's really the Cartan subgroup.
Right.
Non-abelian.
No, you can. So maybe I can take this discussion maybe a little in slightly different direction. You can. There's in this world there's a notion of roots, and then which sometimes corresponds to which is really kind of a just really generalizes the classical notion of roots, and it gets you. Sometimes corresponds to roots, sometimes it corresponds to the really true generalization. And what you always get some version of a quantum while group associated to these roots, though it's not reflection. These are not root system in the sense that there are reflections along the hyperplanes. There are more operators. It's like pi one of the complement. So there's operators of kind of going around. So maybe the squares of the quantum reflection. So these operators you always get. These operators you get in general, but sometimes these guys really are the quantum while group of a certain non-abelian group, like you said. And then of course that with the Cartan generates everything. So in principle you do get algebras which looks like they might be. So a quantum while group is not really a while group. The operators don't square to one, but it's some particular. It's like a. Anyway, it's something which is in the case when it corresponds to when the root hyperplane arrangement is special, namely it really corresponds to actual roots of a finite dimensional Lie group that you would get like a quantum while group of that Lie group, and so you would see that enhanced symmetry. But in general, like I said, it's some very complicated algebraic structure. It looks like some particular. It's a groupoid of some particular kind, so which would kind of generalize its reflections in the hyperplanes in ordinary theory.
Okay, I had enough questions, and let's take Andrei again.